over to Dan.
Kelly, thank you so much, and thank all of you for joining us today for session number 5 of 2023's Varitec Technical Institute Lunch and Learns webinar series. Today's presentation is on the physics of airflow and fan system effect. My name is Dan Hahne. Excuse me, my frames are not advancing. There we go. My name is Dan Hahne. I am, as Kelly had mentioned, a Director of High Performance HVAC Solutions here at Varitec. I've been in the industry since 1985, so it's going on 37, 38 years. And in 2008, when I entered into engineering sales, I decided to really devote myself and efforts to high performance HVAC systems. I joined Varitec in 2016 as their educator and have served here ever since. So my focus really with regard to engineering sales has been education with special attention to high performance systems and soon to be greater attention on indoor air quality. This August in Engineered Systems magazine, I was able to have another opportunity to co-author another article with 2 engineers out of PAE in Oregon on the rather innovative and creative building, the Helios Foundation on 32nd Street in Camelback. The article goes into detail about an innovative approach and design for active chill beam systems. So if you have the interest in time and availability, I suggest that you might want to look at the article. Today's agenda, however, is on fan system effect. And we're going to cover multiple items regarding system effect. But first of all, we're going to look at AMCA 210 and standardizing fan testing methodology. And then we're going to look at AMCA 201 and what that document says with regard to calculating system effect when we're confronted with that condition. We're going to learn how to read fan curves. We're going to look at the causes of system effect. We're going to look at conditions resulting in system effect, the tools to calculate the effect, best prevention, and then we're going to walk through a scenario that illustrates how best to use AMCA 201 in calculating system effect. So first of all, AMCA 210 and standardized fan testing. Who is AMCA? Well, AMCA is an independent testing organization that writes the testing methodologies fan manufacturers and manufacturers of other products must conform to when generating the ratings and performance of their equipment. And if their product is tested in conformance to AMCA prescriptive measures, then they can achieve an AMCA seal, providing those products maintain those performances as long as they choose to carry the seal. AMCA is very good for the industry. I know for fan manufacturers we represent, and we would only represent AMCA certified manufacturers, that at any time AMCA can walk into their facilities, pull a fan wheel off the assembly line and take it back to AMCA to test it. And in the event that that fan wheel fails to meet up to the published performance data, they run the risk of losing their certification. So it's a very effective, very good institution that we lean on for helping make sure that manufacturers' posted data is credible. For fans, AMCA has published a number of standards. The 2 standards we're going to focus on today are AMCA 210 for laboratory methods of testing fans for certified aerodynamic performance. Then we're going to look at AMCA 201 on fans and systems and how installed fans can actually result in system effect and how to calculate using the standard what that effect is. So AMCA 210, what is AMCA 210? The purpose of the standard is to establish uniform test methods for a laboratory test of a fan or other air-moving device to determine its aerodynamic performance in terms of airflow rate, pressure drop, and power consumption. They also define the tools and instruments that are to be used in generating that performance data. So AMCA also has written the specifications for the actual building of a certified AMCA test chamber. And the three fan manufacturers that I've been to throughout my career, Penberry, Greenheck, and Cook, all of them have their own in-factory AMCA certified test chambers that can be inspected by AMCA at any time. And they are designed in a very certain way. When a fan is actually tested, it is the fan wheel that is being tested on the fan. How effective is that wheel in capturing and throwing air down a duct? So in testing a fan, certainly in a supply air application, as illustrated in this photograph, you can see that there's a straight duct section downstream of the fan outlet. That is so air can enter the test chamber at a uniform velocity profile so that all the readings are appropriately assessed throughout the cubic volume of the chamber. So in order for this, for the test to occur for a supply fan, Kelly, can you see my cursor moving? Yeah, okay, thank you. So if we put a fan in a supply air test configuration at the inlet of a test chamber, you'll see that the chamber is comprised of a large box with a supply fan ducted at the inlet of the box, and then there's an exhaust fan at the opposite end of the box, and there's a variable frequency drive assigned to each fan. So when a fan is to be tested, the fan is actually turned on at the same time as the exhaust fan at a fixed RPM, revolutions per minute of the fan wheel. The exhaust fan speed is adjusted so the internal pressure drop throughout the certified test chamber equals zero pressure. And then an airflow reading occurs at that point. Well, to generate how the supply fan performs at various static pressures, there's a wall of nozzles, calibrated Venturi nozzles, that are sealed off one at a time to create static pressure drops and 0.1 inch pressure differentials. So as nozzles are closed and static pressure is incrementally increased, airflow ratings are taken at each static pressure and then plotted. The exhaust configuration is just the opposite. Instead of putting the fan that we're testing on the supply, we put it on the discharge side. We put a supply fan at the inlet with a variable frequency drive, zero out the static pressure throughout the chamber as we take our first initial test reading, generate that CFM, that airflow rate, and then begin to add static pressure to the system in 1/10 of an inch increments, read a airflow at each of those static pressures, and then generate the appropriate data in fan curve resulting from that. Per AMCA 201, fans are actually tested in 4 types of configuration. Type A, which is a free inlet and free outlet. You would see that in a DWDI fan in the old field-built custom air handlers that we built really before the 2000. We don't see them very much anymore. There's installation type B, which offers a free inlet and a ducted outlet. There's an installation type C with a ducted inlet and free outlet, and an installation type D with a ducted inlet and ducted outlet. Whenever a fan is actually turned on, a utility vent set blower, however, notice how the discharge velocity profile is not uniform as it exits the fan outlet. the air actually holds to the surface of the interior of the housing and thrown out of the fan at a higher velocity at the outlet. And then it takes a certain amount of straight duct diameters, known as the effective duct length, in order for that discharge air profile to maintain or hold a uniform profile traveling down the duct. And that is very important, because to get proper fan performance, you want to make sure that you're achieving that uniform profile before it leaves the duct. An inline fan, certainly a direct drive inline fan, as well as a belted, because there is obstruction in the interior of the fan. The velocity profile is different, but the logic is the same. In order to obtain the assigned performance value with that fan design, a length of straight duct is needed at the discharge of the fan for a uniform velocity profile to occur. So if we look at a utility vent set, you will notice that it is actually divided. There is a baffle plate, part of the housing, at the lower end of the discharge. And the reason for that is, if you look at the illustration in the lower right, without that baffle plate, as air is thrown at high velocity and hugging the sheet metal duct, then a lower pressure zone occurs at the opposite side of the duct, allowing air to be sucked back into the fan and thereby starving the actual airflow of possible air. So a plate is always provided on the discharge of a utility vent set to prevent that backflow from occurring. The relationship between the outlet area and the blast area, which is the area the air exits the fan, is called the blast to outlet area ratio. And that is a very important ratio when we begin to apply AMCA 201 in calculating system effect. So how to read a fan curve? How is a fan curve generated? Well, let's go back to AMCA 210 and see what the methodology is applied for generating a fan curve. So AMCA 210 defines what the fan performance curves are and how they're to be obtained. Fans are tested at a given RPM, and they are tested under ideal conditions. So if a fan is being tested in an AMCA certified 210 fan chamber, a fan speed is assigned at a fixed speed, 1200 RPM, 1600 RPM, 1800 RPM. And based at that fan wheel rotation rate, we start at a zero pressure drop through the test chamber, as I had mentioned before. And then in 1/10 of an inch increments, start adding static pressure. So as static pressure is added to the system, the new airflow rate is measured, and we notice that there is a reduction in airflow rate. And a curve forms as we continue to add static pressure until we reach the top of the curve, which is known as the stall point. You never select a fan with a performance point that is near to the top of or at the top of a stall point, because fan stalling results in reduced performance of the fan. It can result in excessive vibration, excessive noise in various conditions. So that's how the fan curve is generated, measuring airflow rates at varying static pressure increments in 1/10 increments. The curve in black is actually changing the fan RPM. It's called the system fan curve, and changing the fan static pressure, or changing the RPM while maintaining a constant static pressure and reading the airflow rates in that manner. So looking at a fan curve, if we look at the curve that shows or illustrates the airflow profile at a constant RPM under varying static pressures, we can understand how much airflow we achieve when we take the projected static pressure of a system, of a ducted system, draw a horizontal line to the RPM fan curve, drop a vertical line down, and we can calculate how much CFM is that fan wheel is able to provide or supply at that given static pressure. The reverse is also true. If we have a fan wheel with certified data and we know we're getting this much CFM, if we look for the point of intersection with the fan curve, we can then calculate the static pressure drop in the system. So, what is system effect? The system effect is the change in fan performance due to an installation configuration that is not the same as the rated standardized test configuration. In other words, all installed exhaust or supply fans suffer from system effect. So what are the causes of system effect? Well, first of all, let's look at how system effect impacts fan performance. It will decrease the amount of flow the fan can otherwise provide when it does not occur or is taken into design consideration, can cause excessive vibration, increased noise levels of the fan, can result in greater fan energy consumption because to overcome it, it is frequent that you increase the fan RPM, providing the motor horsepower is available to do that to a certain point. And of course, during startup and commissioning, it results in a lot of field time trying to assess why they're not getting the generated airflow per the design conditions of a project. So, AMCA 20102 is the standard that actually assesses the causes of system effect, and it is published to introduce into the market what is known as a system effect factor that is generated when system effect occurs. A fan system effect factor quantifies the duct system design effect on the performance of the fan. It is a value that accounts for the effect of conditions adversely influencing fan performance when installed in the air system. Well, there are three common causes to fan system effect. They are improper outlet connections, non-uniform inlet flow, and swirl at the inlet. And we're going to look at each of these conditions individually. Improper duct conditions at the outlet of the fan. These are conditions that result in a restriction of airflow, resulting in decreased performance, and is generally associated with outlet system effect. These conditions result in a different aerodynamic behavior of the fan impeller, and it generally is associated with inlet configurations or blockages. And then there are duct systems that are installed in the non-ducted configurations. So in order to avoid or minimize system effect on the outlet of a fan, we need to make sure that there's a significant length of straight duct at the discharge of the fan in order for the airflow to achieve a uniform velocity profile. If you do not have sufficient duct length, as this diagrammatic suggests, or this list of 3 duct lengths that allows for optimal performance of airflow, and we begin to add a transition of some type before the effective duct length, you will have a decrease in available airflow as these curves demonstrate. They're all the same RPM, but if you notice, if you change the effective duct length, or if you provide a transition before the effective duct length is arrived at, you will reduce the amount of airflow capable of that fan is able to provide. So let's look at a fan curve that we would anticipate on seeing generated from AMCA 210. Here we have our RPM fan curve, the airflow rates along that curve in relation to the static pressure. Now, when we have system effect at the outlet, we notice that we are not getting the airflow that we had originally intended from that fan. It is reduced. And the differential between the AMCA 210 performance and the field measured condition based on an outlet condition of the fan is called your system effect factor. And we will look at that factor in greater detail later in the presentation. So if we look at an AMCA 201 example or an application of an AMCA 201 system, and how do we apply it? Well, 201 has charts that actually show how system effect can be calculated. It'll actually generate the calculation. The first thing you need for a blower is to make sure you understand what the blast to outlet area ratio is. And every fan manufacturer has those ratios available. Once you know what the fan to outlet or the blast area to outlet area ratio is, you then look at what the duct configuration is at the discharge of the fan. Here we have a blower, which we see commonly in Phoenix, and we see that is a non-ducted discharge. So in looking at the fan system effect fan curve and knowing which curve to assign to the performance of this fan arrangement, we look at AMCA 201 tables, we look at the no duct configuration, we look at the blast to outlet area, and we find and locate which system effect fan curve to apply to the performance of a fan manufacturer's ideal performance conditions. Well, under this condition, seen in the photograph, we notice that we would use system effect fan curve R and S. If we go to that fan curve on the 201 fan curve chart, and we look at the discharge velocity of a given fan, which we would say is approximately 2400, 2500 RPM, and draw a line vertically up from that fan speed up to intersect with the system effect fan curve, and then draw a horizontal line over to the y-axis, which is the static pressure associated with these curves, then we notice that due to this configuration, an additional 0.4 inches of static pressure needs to be added to the fan in design phase, so adequate horsepower is provided in order to overcome the system effect, allowing the fan to discharge the necessary outside air into atmosphere. And we're going to look at this configuration again later in our presentation as an example, because reducing that static pressure drop can occur very easily by adding a length of straight duct at the discharge. So anyway, there's an example on how to apply AMCA standard 201 for assessing the static pressure gain due to outlet system effect. So when you're actually designing fans, or when an engineer is designing fans and the ductwork connected to the fans, the engineer needs to pay attention as to where duct transitions are in relation to the outlet of the fan. There is a very severe condition occurs that when a 90-degree elbow or even a 45-degree elbow is placed or is connected to the discharge of the fan in an opposite direction of the rotation of air. If you do that, you create a condition known in the industry as breaking the back of the fan. The high velocity discharge air exits the outlet of the fan, hits the back wall of the duct here, and bounces back in, impeding the proper flow of air throughout the duct system. So in the event a building's layout and design does not allow for the effective duct length to be incorporated into an exhaust fan design, then an engineer needs to realize that if a transition is required before the effective duct length is achieved, that they make sure they do it in a way that it follows the directional airflow at the outlet of the fan. It'll still result in system effect, but it will minimize system effect. Now, in looking at a fan that's installed, a utility vent set that's installed on a roof, it is often asked, how do you identify which rotation or how the fan is actually rotating in that fan? Well, the best way to do it is look at the wheel, the actual motor side of the fan. And you always look at a utility vent set from the side of the fan that the motor is located in order to assess whether or not the air is flowing clockwise or counterclockwise. So just something to be aware of if you're looking in the field at utility vent sets. Well, does breaking in the back of a fan duct arrangements actually occur? And the answer is yes, absolutely they occur. And if it's installed like this, it is not going to be a good day because it's very expensive to correct, especially for larger fans, because those housings are welded to their frames, and you would have to grind off all the welds to turn the frame, and now you're reducing the effectiveness of the coating of the fan, etc. And it's a very big problem. From my experience in actually sizing and ordering these fans as a salesperson in this industry for a number of years, I'm more inclined to think that inappropriate connections like this was a lack of coordination between the representative and the contractor. Many engineers know perhaps not to design fans in this configuration, and I always recommend that coordination occur with the manufacturer, salesperson, and the contractor to make sure they're assigning the appropriate orientation to utility vent set to prevent this condition from occurring. Again, look at this configuration and how expensive it would be to actually change it on the roof, especially if there was no space on the roof to do that. You'd have to reorder the whole fan, and then you'd have to crane it up or whatever. So this condition does occur. It's not uncommon in the field that there's inadequate or inappropriate coordination between transitions and the outlet of fans. It actually occurs in Phoenix, Arizona, and this is a rather innovative approach I've found, but illustrates very clearly that this duct configuration is more than likely to result in significant system effect and consequently reduction of airflow capable of that fan. Another condition that causes system effect is non-uniform inlet flow. What is non-uniform inlet flow? When air is traveling down a duct and it encounters a transition, such as a rectangular 90-degree elbow, air with a uniform velocity profile hits the back of the duct wall here and then results in a high velocity flow at the air as it's traveling along the wall of the duct. And the inside transition sees a negative pressure zone forming. And consequently, before you can really measure the amount of airflow in that duct system, you have to give it room, you have to give it space for it to achieve a uniform duct velocity. Well, if you do not have that uniform velocity at the inlet of a fan, what will happen is that the fan wheel itself will not load properly and uniformly, and consequently it will restrict the amount of air available to be discharged from that fan. So you want to make sure you have uniform air velocity loading a fan wheel. And then there's swirl at the inlet. What is swirl at the inlet? If you look at a transition that might be close to the inlet of an exhaust fan, and it's necessary due to architectural restrictions, at least minimize the effect. You want to make sure as the air moves around a transition that it's moving in the general direction of the rotation of the wheel so that the wheel can more effectively pick up the air as it's entering the inlet of the fan. If you have air swirling in the opposite direction to the fan wheel rotation, it will maximize the amount of system effect by increasing or by decreasing a uniform flow profile at the inlet of the fan, and the fan will not load appropriately, and you'll have significant reduction of airflow rate. So what are the tools available to calculate system effect? How do we know what has to happen in the field when system effect is encountered, either through perhaps inappropriate duct design due to restrictions of architectural limitations of a duct system, due to a contractor not carefully following the drawings as they're laid out? How do we apply AMCA 2.1 to understand system effect? Well, to avoid conditions of system effect, it's just not always practical. So consequently, we want to go ahead and apply AMCA 201 and the 201 fan curves to assess what that effect might be. So let's look at an example. Let's look at a roof-mounted vent set or utility vent set. We're going to look at an example here of a fan that is a Penberry 222 VCR utility vent set designed to provide 12,000 CFM at 2 inches of static pressure. The outlet velocity of this fan is 4,200 RPM, and I'll ask that you remember that value when we apply the system effect fan chart. The blast to outlet ratio of the fan is 0.7. The fan speed itself is 2,016 RPM with an operating brake horsepower of 12.35 brake horsepower. In this configuration, would you anticipate system effect to occur? Well, AMCA 201 has a chart that identifies transition locations at the discharge of a fan. And with a rectangular outlet, there are four positions, position A, B, C, and D. The discharge position of this fan, as you've probably gathered, is position C, where the outlet of the hood is in the opposite direction of the rotation of the fan wheel, causing some form of system effect. How much system effect? Well, let's apply the 201 system effect fan chart. Again, let's identify the blast to outlet ratio provided on a fan submittal. Let's look at the outlet elbow position. We've assigned it position C. We've noticed that there's no duct work beyond the transition, so no outlet duct. That means that to assess the static pressure gain or the fan system effect, we would want to apply system effect fan curve P. So looking at system effect fan curve P, at a fan that has a discharge air velocity of 4,200 feet per minute, where that vertical line intersects with system effect fan curve P, and we draw a horizontal line over to the static pressure gain, at those conditions and that duct configuration, that system effect is equal to 2 inches of static pressure, which is significant. Now, having said that, 4,200 feet per minute discharge velocity is extremely high, and it could be very noisy, but I did it to demonstrate really what this actually means. And that, yes, you can have significant static pressure drop with the inappropriate duct configuration at the outlet of a fan. Well, in the event system effect occurs, then how much does a fan wheel need to be sped up in order to overcome the system effect? Well, we calculate that by using the fan curves. And these curves you can take to a court of law. In fact, the AMCA 210 fan curves are based on tests of a fan wheel of 1 RPM. And then the other performance points at other RPMs are generated by applying the fan curves. They don't test every RPM available to the fan to look at airflow rates. They do it at 1 RPM and then use the fan laws to calculate airflow rates at varying RPMs. So if we look here, though, at static pressure differential, that the fan speed is affected by the square of the differential. So all of a sudden we see that that fan might need to speed up considerably. And if you speed up the fan, what does that mean for the horsepower? Well, the horsepower is the cube of the RPM differential. Depending on how much static pressure gain, you may have to increase the size of the motor horsepower, which means you would have to look to see at what electrical is available to service that horsepower, if it is available. And if it's not, that means you have to change out the electrical to that fan. So the dominoes start falling very, very quickly when duct configurations are not properly addressed or seen to, either in design or installation in the field. So good duct practice with regard to outlets is make sure that you have less than a 7-degree divergence should the outlet be smaller than the duct size itself. You have a less than 15-degree convergence if air has to be injected into a smaller duct due to architectural restrictions. And always, always, always apply turning vanes at the transition as necessary. Poor practice, you can see here, is illustrated very clearly by removing transitions at the outlet of the fan to reduce system effect. So what about round duct? The same thing applies as well, but instead of using the other fan curve or the other system effect fan chart, we actually used one for round duct works. It has a different profile and characteristic, so that instead of using the blast to outlet ratio, we use the radius to diameter ratio to allow us to locate which system effect fan curve to apply to round duct configurations off of round fans. So if you look at system effect fan curves and what they mean with regard to a lack of straight duct on the outlets of round fans, we can see here that having no duct before the transition results in a system effect fan curve that has a higher pressure drop assigned to them at performance than increasing the amount of straight duct at the discharge. So again, following AMCA 210's recommendations, always design with the straight duct necessary to create uniform flow rate. And then also be aware for inlet swirl to reduce and minimize, if not eliminate inlet swirl, always, always use turning vanes at that transition. And you can see that very clearly when you look at the 201 system effect charts. And you will notice that for square duct with turning vanes, you can use a system effect fan curve that results in lower pressure drop than others should turning vanes not be assigned at those locations. And they also apply too for round radius system effect fan curves. And if we look here, look at the differential of which fan system effect curve needs to be utilized for a system that does not use turning vanes at a transition before the effective duct length. It is significantly greater than a transition that has turning vanes, even if it does not reach a distance of being beyond the effective duct length of that fan. If you looking at round ductwork again to reduce system effect, you want to look at, instead of hard 90 round elbows, look at mitered elbows. Increase the number of miters in that elbow so the transition occurs more gradually and it allows for a more effective transition into the inlet of the fan. There are conditions that in a field in mechanical rooms that you just don't have the real estate to put enough effective duct length for fans to minimize system effect. Consequently, I suggest certainly for utility vent sets in those conditions, work with the fan manufacturer that's being laid out as basis of design. The fan manufacturers that I've worked with have actually can provide inlet plenums that are designed in a way that actually minimize static system effect at the inlet of a fan. And I would recommend working with factories to build those for you as opposed to a contractor building it in the field who really doesn't have the resources to draw from and how to actually design the appropriate inlet condition to reduce system effect. So with regard to inlets and the best design practice, we noticed that you want to have a less than 7-degree divergence from an exhaust duct coming into a fan with a larger opening, less than 15-degree convergence if the duct is larger than the inlet of the fan, and always maintain 3 to 5 straight duct lengths before the inlet of the fan wherever possible, but use AMCA 201 to help assess system effect if there is not the architectural space available to get the effective duct length. And again, here are some poor practice design configurations at the inlet of the fan that will restrict airflow. The same applies for inlet fans as well. Standard 201 has illustrations that show appropriate configurations for fans should transitions be in the immediate vicinity of that fan. Notice that DWDI fans in conformance to arrangement D also have considerations. There has to be a minimum free area between the inlet of the fan and whatever wall of the room that fan is being installed in. You don't want to restrict the free area available to the inlet of the fan, or it will reduce the amount of air available at the inlet for it to be moved by that fan. So the best prevention for system effect, how do we prevent it? Well, we try to avoid creative duct designs that can often occur in the field, either through a lack of coordination in the field with the engineer or for whatever reasons. They certainly do occur, and there's a lot of demonstrated cases to show it. These are very creative duct configurations, no question about it, but somehow or another, those fans will not be supplying the air that they are capable of providing at properly designed conditions. There's a common condition of system effect that we see now that air handlers are using fan wall technologies or fan arrays. An excellent decision in an air handler design to maintain uniformity of flow throughout the air handler and proper loading of cooling and heating coils. Some of the fan wall manufacturers use blower assemblies, use backdraft dampers at the inlet of each module. In the event that a fan should fail, the damper will close and prevent backflow from the supply air chamber from entering that now dead opening and coming back into the mixed air section of the fan. Well, please be aware that Ruskin's, a leading manufacturer of damper products, does warn about using backdraft dampers in fan wall arrays because they are not designed to be located at the immediate inlet of a fan. They will result in system effect and should be taken into consideration. And if the fans are variable speed, then the free area at the damper will adjust as well. So its impact on flow will depend on the flow. So be aware that there are manufacturers out there that do make zero pressure drop inlet backdraft dampers that are designed to reduce pressure drop at the inlet of fan walls and fan arrays. So you're not challenged with the restrictions conventional backdraft damper technology will present within a system. So be aware of that. So with that being said, in reviewing AMCA 210, reviewing AMCA 201, the causes of system effect, how to calculate system effect when it occurs, let's look at a practical example on how AMCA 201 can be applied. And by the way, you can download it for free off the internet. You don't have to pay for it. It could be a good document to have on hand for contractors and engineers when fan systems, either associated with supply or exhaust fans, or even the fans of air handlers or fan coil units, are not generating the flow rates the design requires. So let's look at the phone call. I've been at the receiving end of this conversation in the past throughout my rather long career in the industry, and being approached by a contractor to say that the fan doesn't work. Well, if a fan is short of airflow, I can assure you 90 to 95% of the time, if not more, it's not the result of the fan unless there's a faulty motor, a faulty VFD, or whatever. Again, the flow rate is dependent on the fan wheel at a given RPM. And what that RPM is and the airflow generated at that fan speed is in relation to the system static pressure drop. So anyway, somebody gets the phone call. The contractor, who's understandably irate because they have to complete a job and they're going through startup and commissioning, and now all of a sudden we hear that the 3000 CFM fan ordered at 1 inch of static pressure is only generating 2500 CFM at 3/4 of an inch of static pressure. Your fan doesn't work. I suggest for any manufacturer's salesperson or representative who is on the receiving end of that phone call, get on their bike and go to the job site or have photographs sent of the actual installation of that fan, because a drawing shows how a fan should be installed doesn't mean that that's how it is actually installed, and I can testify to that fact. So the first thing you need to do when there is a shortage of flow performance is the field installation needs to be inspected. Let's look at the actual design of the fan for this sample configuration. It's a utility vent set designed to provide 3000 CFM at 1 inch of static pressure. The outlet size of the fan is 13 by 13. The blast area is 9 by 13. There is no duct length at the discharge of the fan. And the fan discharge velocity is 2,556 feet per minute. The blast to outlet area ratio calculates out to 0.7. So let's look at the condition. Let's look at the effective duct length that is required, which is 4 feet in order for the fan to hit a uniform velocity profile. So there is no effective duct length at the discharge of that fan. So consequently, we go to AMCA 201 charts for rectangular outlet utility vent sets. We look at the blast to outlet area, 0.7. There's no duct at the discharge of the fan. So consequently, to assess the static pressure gain due to system effect, we use system effect fan curve S. So looking at the 201 system effect fan curve chart, we look for the discharge velocity of the flow. We look for the system effect fan curve to be applied, curve S, and where the vertical line off of the velocity intersects with the fan curve, we draw a line over to the static pressure line, and we see that there is 0.3 inches of static pressure added to the fan because of a non-ducted outlet. So what is the normal result of that? More often than not, in my experience, is, well, we got to speed the fan up, or we've got to increase the horsepower to overcome this. And in order to do that, we evaluate various fan curves or whatever to overcome the airflow deprivation by the fan. Well, let's look at how we can use, instead of going through all those permutations and the time involved for assessing what that new flow rate might be, let's just sit back and look at AMCA 201 system effect fan charts. Let's look at what if we added some straight duct length at the discharge of the fan? What if 12 inches of just straight duct is added to the discharge of the fan? That means that you can now use 25% effective duct length out of the 4-foot effective duct length we calculated. By doing that and looking at the blast to outlet area ratio, we see that system effect fan curve W through X can be applied. So if we go now to the system effect fan curve and we apply the W fan curve, we see that it does not intersect with the velocity, the vertical velocity line. So consequently, system effect is eliminated by putting a straight piece of duct at the discharge of the fan, a far more economical, easier, faster approach to address that. In actual designs, any engineer who's joining us, if you're laying out utility vent sets, make sure you have some element of straight duct on the discharge of that fan so you don't have unforeseen static system effect, static pressure additions to your system. So the next time you have a challenge in the field with creative duct designs and creative installations, please remember to use good design practice for your ducts. Apply standard 201, lean on your fan performance curves as prescribed by AMCA 210 and how they're generated, and make sure that you maximize the straight duct lengths at the inlet or the outlet of a fan. Make sure that the transitions are properly orientated to reduce the amount of system effect, and then use 201 to calculate the static pressure gain in a system where there's not the space available to provide the ideal conditions, but at least now you have a fan designed with the horsepower necessary to create the fan flow rates that you are needed to meet the building requirements. Any questions?
So as of right now, there are no questions in the chat. But if you do have any questions, feel free to pop them in there, or you can come off mute and ask.
Pretty quiet, Kelly?
It is.
I don't know if that's a good thing or a bad thing. I much prefer giving these in person because you just can't enter into the dialogue that, but we do the best we can with what we have. So,
We have a question. What effect do sound attenuators have?
Sound attenuators will also provide system effect as well, because a sound attenuator is going to have baffles throughout the middle of them, and those baffles will impact the actual flow. Not to mention, a sound attenuator is going to have its own static pressure drop that is to be assessed. Yeah, sound attenuators will impact fan flow, but any sound attenuator manufacturer will have the pressure drop ratings based on inlet velocities, and you can include that into your fan design. So good question.
And they will also have recommendations of the install and how much straight duct as well.
Correct.
All right. We got questions. How many manufacturers have straight pieces of duct made at the factory for the outlet?
I think you can provide a straight duct length from the manufacturer. I'd have to check that. I'm going back a number of years since I was doing this. But I think manufacturers do offer outlet extensions for their fans. And if so, and you're not infringing upon any height restrictions of mechanical equipment on a roof, I would certainly apply them wherever you possibly can, because they're a minimal cost.
What about a system out of power, full motor amps at near design static set point, but the flow is still short? What are some ideas or places to look into?
If you're getting the amp draw, but you're short of airflow, then that would suggest another condition that occur outside of system effect would also be duct leakage. If the fan is moving at a given RPM and you're not getting the airflow, then there could be, certainly in a supply configuration, duct leakage going on because you're still moving the same amount of air from the fan. That would be one other consideration.
He said no leakage.
Oh, no leakage? Okay. Then I would say, now is it a ducted on the inlet, on the outlet? You would really want to look at what transitions could be impeding that flow, because just keep in mind that that fan is tested under ideal conditions. So there has to be some type of impedance of flow or some type of aerodynamics within the duct at the inlet of the fan that is preventing the proper loading of air on that fan. So is there a 45-degree elbow? Is there a 90-degree elbow? Where does that occur? Also, I was actually encountered a system a number of years ago of a large energy recovery unit that the duct system was so extensive that the fan just didn't have the capability to draw air to the design points of each location of an exhaust grill. The duct system was too complicated to do that. Even though the static pressures were in line, you just couldn't speed up the fan fast enough in order to overcome the system resistance. And I seem to remember as well that just below the roof, there was a 90-degree duct transition that just added to the difficulties. So if there's insufficient airflow, think of it as being restriction. That's the only thing that can happen other than uneven loading of the fan wheel at the inlet.
Okay. Brian, you have his contact info, so if you guys want to take it offline, you can.
Okay.
That is it in the chat. But again, that goes out to everybody else. If you have any specific questions and you want to walk through any scenarios that you need help with, Dan is the man.
Kelly, thank you very much. And thank all
You're
of you for
welcome.
joining us today. And if you think of any questions, as Kelly mentioned, don't hesitate to forward them on to us. We'll answer them.
Absolutely. Thank you all for attending. I will follow up with an email with the PDH certs and the recording. Have a
Thank
good day.
you so much. We'll see you in October.